Hello, everybody. Welcome back. We are here for, it feels like it's been a while. I didn't do a hangout last week because I was away at a workshop in California, so I couldn't do one. But welcome to this month's Footsteps to Mars hangout. My name is Tony Darnell. I am from deepastronomy.space. Let me just put that up so I can prove it to you. And today we're going to be talking about, as we always do in these hangouts, humanity's efforts to go to Mars. What are we doing? What's NASA doing? What are the various corporations doing? Things like that to help us get on the planet Mars. And today we're going to be talking with people from NASA Johnson Space Center as well as NASA HQ to talk about the efforts of the role that the International Space Station will play in helping us get to Mars. So, and as we do each week, let me just say a couple things before I introduce my co-host. We are streaming on YouTube, Facebook, Twitch, and Periscope, and I have my good friend Carl Clark back. He is helping us with monitoring all of this stuff, so we will be able to see your questions and comments on all of those live stream channels, so we encourage you to do that. So it's time for me to bring up my guests. And with me, let me start with my co-host, Dr. Harley Thronson. He is at the Goddard Space Flight Center. Hi, Harley. Welcome back. You've been a busy person, too, these past few months, or weeks, I should say. I have
been a busy person due to a large part to the two guests that we have this afternoon, as we'll be talking about shortly.
They've been keeping you busy, huh? Let me apologize, folks.
Colleagues like that.
Okay, let me apologize.
One of the reasons that we brought them up.
What's that?
No.
Oh, okay.
Please go on.
All right. I'm sorry about that. I just want to apologize in advance. I have a head cold, and I'm sorry for the nasally sound of this particular hangout. The good news is, though, because we do all of this remotely, I'm not busy making everybody else sick, so we can keep going with the hangout. So my apologies in advance. Hardy, why don't you give everybody a quick introduction into the hangout series itself, just very briefly, and maybe an introduction into our topic today, as well as mention who our sponsors are, things like that.
Yes. So welcome, everybody. And we will give credit to our pair of sponsoring organizations, the two AASs, the American Astronomical Society and the American Astronautical Society. Their generosity allows us to keep on with these series of hangouts. So thank you to them. The first Thursday of every month, we have a hangout on what we refer to as Footsteps to Mars. So what are the technologies, the capabilities, the motivations, the challenges, and so on, in robotic and eventually human exploration of the mysterious red planet. But if ever we're going to go to Mars, we're going to have to take those first initial footsteps, and that's why we have two of my colleagues on today. That first step is, of course, the International Space Station. It's been an enormous engineering and increasingly scientific success, and many of the experiments on there and the technologies being developed on there are critically important before we expect to send humans on the long duration, enormously challenging mission one day to Mars. So let's get started.
And the AASs?
And I already said the AASs. The American Astronautical Society and the American Astronomical Society.
Okay, good. Just to make sure.
I did. It was the first thing I said.
Excellent. Okay, very good. I'm busy pushing buttons. I can't always go. So that's why I'm not pushing buttons right now.
Not so much NyQuil.
Yeah, exactly. Okay, so my guests today are, as I said before, both from NASA HQ and the Goddard or Johnson Space Center. I have Dr. Katie Boggs. She is in the lower left part of the section here. Hi, Katie. She is part of the ISS division and the technology demonstration unit at NASA HQ. So welcome, Katie. It's good to have you on our hangout.
Thank you.
Okay, and also at the lower right is Dr. Molly Anderson. She is in life support development at Johnson Space Center, but she's physically at the NASA HQ because she's on travel. She's been working, I guess, on this workshop that is keeping Harley so busy. So welcome, Molly. It's good to have you as well. So let me start with Katie. You're working with the ISS division at NASA. Tell us a little bit about what NASA and in particular the ISS's role might be in getting us to Mars. What are you guys talking about there at HQ?
Might be or is. Because, I mean, we are already, right now, starting to get ready to go to deep space and eventually to Mars using ISS. So I'll go with is.
Okay, go ahead.
To answer my own. So, you've probably heard a lot about the Scott Kelly, the one-year mission and the twins study. And that's just one piece of the types of things we're doing. Because ISS is a great platform to allow us to understand the impacts to the human, number one, on being in deep space, or being in space in general, but give us some idea about what to expect for a long mission, such as what we would be doing to go to Mars. But it's also a good opportunity to test technologies that we need in a relevant environment. And so, in particular, ISS, we really have a good experience there with life control systems. How do you keep, the astronauts able to live and work in space? But we designed that around a situation where we have, we had space shuttles, and now we have Soyuz vehicles, and we have cargo vehicles that can bring us supplies all the time. So we're moving into a regime, and we've already started testing some of these systems that would enable us to go further where you don't have regular resupply. And in fact, that's part of the why my friend Molly's here, because Molly's her area is responsible for about 2/3 of what we're doing to get ready for deep space in terms of the technology.
Well,
so
okay.
I think that's a short. We can get into it more later, but I'd love to let Molly.
Okay, go ahead, Molly. You have something you want to add to that with what you're working on?
So I guess the experience that we've had on the International Space Station with our environmental control and life support systems, they were developed obviously by a dedicated group of people who tried really hard to get everything right. And ISS has taught us technical things about the hardware, but it's also taught us things about what is hard to test and evaluate on the ground. And since part of the, a critical part of the mission to Mars is that long transit in microgravity with not really much feasible abort, there are things that we need the ISS to be a long duration, stable platform with realistic humans putting realistic challenges on the system to gain the confidence to say we're ready to go.
But it's not quite the same, is it? Because of, ISS is getting regularly resupplied. How accurate can you go with making the ISS a sort of a simulated platform for long duration space flight? I mean, I know that there were, that at the astronaut Kelly experiment was to see the long term effects, and that he also had a twin, I believe, that we could compare things to, which was interesting. But beyond, I mean, are there limits to what the ISS can do to realistically demonstrate long duration Mars trips?
Yeah, certainly there are limits. I mean, you'll never have a perfect representation of a Mars mission until you're on a Mars mission. I think that, and there are some risks that we do see, until you design the power system or the software systems for your final Mars vehicle, you may not be getting those exactly right. I think you have a spectrum, though, in terms of how much you want to torture yourself now and how much you can afford to do that for how good you want it to be. We could tell the astronauts that they're not allowed to eat any of the ice cream, any of the oranges, any of the fresh food resupply. We could send all of their food up at once and not send them any more of that resupply and just see how that goes, right? But that starts to hamper other objectives, like happier people probably get more work done, and we want them to be doing all of those science experiments and all of those other things on the space station too.
Right.
So a lot of our systems are going to be evolution of the systems that we're using on the space station. Not necessarily
what do you mean by that?
Radical.
What do you mean evolution?
So, right now on the space station, we collect carbon dioxide with a zeolite adsorbent. We put it through a Sabatier reactor to make water and methane, and then we electrolyze the water to make oxygen. That electrolyzer worked pretty good. We're going to upgrade a couple things in it and basically keep that design as is. our carbon dioxide removal system was sort of infamously frustrating. And so we have 3 different systems, 3 or 4, plus the international partners have some, that we're evaluating as a replacement or an upgrade. But we still want all of them to be able to connect to a reactor downstream that turns the carbon dioxide into water. Okay. So many of the same functions are included. And so the challenges that you get in trying to integrate real hardware with real operational hardware can add a level of fidelity that sometimes people, it would still be challenging to set up that simulation on the ground to impart that level of discipline. And we've talked about that in other systems too. You're testing your system and you'd better lock it in a room and put a guard in front of it because you're not allowed to go fix it if it starts to do something, funky. So we can put as much discipline and rigor on as we can afford to do. But really, we prioritize our goals. We're not really as worried about the bolts that connect it to the rack. We're worried about microgravity fluid flow problems inside the system or things like that. And so for those things that matter, we think ISS is a very good demonstration platform.
And Molly, if I can add, I think the other thing you have to remember is that part of the overall system is the human, right? And so microgravity affects the human, and therefore the human's outputs, the waste outputs, the intakes are different because they're in microgravity. So you need to put those environmental control and life support and environmental monitoring systems up there with the humans as they're being impacted by microgravity to get the true effects. And I think you guys have some great stories about how I think the waste and hygiene stuff did not work the same.
Yeah, there's sort of...
We just tested it. So there's good reason to get that test regardless of if it's the same duration because microgravity does impact the human.
Yeah, that's sort of an infamous story.
Yeah.
What was this? So what did these ways you have to? What was the story? Because I
slightly gross story. So we experienced some failures early on with the urine processing assembly. We put sulfuric acid. Well, we originally put sulfuric acid into the urine. Before we process it. We do that to shift the pH, which prevents certain precipitation, and it prevents the ammonia from breaking, or the urea from breaking down into carbon dioxide and ammonia, which would cause bubbles. Of course, bubbles in liquids are bad in space if you want to be able to control where things are going. So we tested this on the ground.
Like carbonation. It sounds like carbonation. Go ahead.
Yeah, carbonation, also carbonated beverages, no-go in space. We tested it on the ground with real urine because urine is incredibly complex. So we got donors to provide urine, and we put the sulfuric acid formulation in it, and then we distilled it to make cleaner water, which then does get processed afterwards. But when we talk about issues that crew members have in space, we're worried about bone loss, right? So if you're losing bone, what's in a lot of bone? Calcium. If you're losing calcium, where is it going? It's a mass balance. It has to exit your body. When you put the sulfuric acid and the calcium together, you get gypsum. So engineers who are motivated to generate enough test fluid to test their system on a regular basis are pretty well hydrated. And crew members who don't have a water recycling system and are trying to manage their stores well and also experiencing bone loss. While both of those are real urine, they have different qualities. And real crew member urine plus sulfuric acid when distilled makes gypsum in your water processor. Oh. And rocks in your water processor are also really not good.
So it clogged it up then.
So we did a short-term intervention to back off and just not distill it as far so it didn't precipitate. And then we have switched from a sulfuric acid formulation to a phosphoric acid formulation that accomplishes the same goal, but doesn't precipitate at the same or as early. And so we can get as much water out of it as we had intended without creating solids inside our water processor.
Okay, and this was all tested up on the ISS then?
Yeah, this was a lot of our regenerative life support system hardware, so the things that recycle wastes back into usable materials were sort of considered proto-flight when they flew. So they knew when they sent them that there was a certain amount of risk and a certain amount of redevelopment that might be necessary, because it was the first time we were trying to do most of these types of things. And like I said, we learned both things about the technology, and we learned where the weaknesses were in our ground test programs. So some things we do a much better job of testing things on the ground now to predict whether they're going to work on ISS because of those lessons learned. But we still had enough unknowns in that process that we want to, anything that's radically new, we want to put it through that again before we trust it.
Okay, now, Uric Mazino has a question. Hi, by the way, hi, Uric. It's good to see you back again. And I'm going to expand on his question, too, but he's asking, are there any tests in the works to address the effects on the top of the brain that occurs during long-duration space flights? And let me just, that's a specific aspect, but I just want to say, Molly, I'm not hearing a lot of good news about the health effects of being in space a long time. Even for journeys, you know, of a few weeks or more. I mean, getting to Mars notwithstanding, even just being out there a reasonably short amount of time is very detrimental. How do you address, first of all, Uric's question about the top of the brain, but in general, are you concerned about sending humans into space for a very long period of time?
So I'm not exactly sure what you mean by the top of the brain.
Well, I think this idea that when you're in weightlessness or microgravity for a very long time, yeah, what is it? I don't recall.
Intracranial pressure.
Yeah, there's something going on in your head.
About the intracranial pressure and there's a cat in Harley's. I think, yeah, I mean, there is research going on into the changes in intracranial pressure or the ocular pressure. So, you know, we know that the eyeballs have some issues. And there's a whole series of experiments called fluid shifts that's looking at those issues, because, you know, when you're standing on Earth, most of the fluids in your body kind of flow or are naturally pulled towards your lower limbs. That's why, you know, when you end up with swollen legs and stuff like that. But it's different. If you look at astronauts when they're in space, they're doing a hangout like this, their faces are a little bit puffy because the fluids are more evenly distributed. Right. So now neither Molly nor I are human research people, but we can fake it a little bit. So, but the human research program at NASA has really put their focus on to the mitigation aspects of those issues. We know a good deal, probably not everything, about how being in space impacts the human. And they still need to do more to understand the impact of long duration space flight. So, you know, the Scott Kelly one-year mission is probably the first of a series, assuming we can get astronauts to agree to stay out there for a year and away from their families and all. But so that's what's going on. Is they're using those opportunities to understand the long duration impacts, and then to also develop strategies to mitigate against them.
I guess there's also a lot of ways in which the technology world is trying to respond to that as well. So, you know, we're talking about making gypsum in the urine processor. That high calcium would also do things like increase your risk for kidney stones. Right. So our requirement for how much water per day we need to be able to provide for the astronauts has changed versus what it was in the space shuttle program. We are trying to do a better job of keeping carbon dioxide down at lower levels, and hopefully new technologies will help that. We don't, the human research program scientists working on some of these questions, but in parallel, we're trying to improve the environment and make things better. For the bone loss and things like that, right? They're inventing new exercise protocols and new exercise devices and figuring out what it is the crew members really need. And on our side, the amount of exercise that the crew is going to have to perform is certainly larger for a Mars mission than it is for a space shuttle or an Orion mission. Different people on ISS have had different experiences. So ISS is a huge volume relative to other spacecraft, so it has a lot of buffer space for transient effects to flatten out. But in a smaller spacecraft relative to ISS, if the crew members are exercising, 2 hours a day a piece or something, that's a big metabolic load for us to clean up. So we need to resize our systems and make sure we're designing to be able to keep them comfortable and keep their environment safe while they're doing all of that. So there are places where a concern about a health problem echoes into a design change or something, or things like that. Radiation risks can be an important part of a discussion of what is the physical shape of your spacecraft, where is your extra water stored. Because if you can put it in a place where it helps protect the crew, that's better.
That is a great segue into Bjorn Larsson's question, and he's asking on YouTube live chat, if we were to build a prototype of the crewed Mars spacecraft, how would it differ from the ISS? Now the ISS is shielded for radiation, but it isn't obviously an ideal shape for getting us to Mars. At least I don't think it is. What are the other components? Like you mentioned radiation shielding as very important. What are some of the other things?
That's interesting. That kind of comes into this workshop we were in, I guess, a little bit, and talking about a range of architectures for getting to Mars. The ISS is designed as a science laboratory, and while I think we want the crew members to have good things to do during transit, and I want to go to the surface of Mars for science and exploration, that vehicle is not necessarily going to be optimized so that your science experiments have the best controls possible, right? That vehicle, the cost of pushing it to Mars is so much larger than the cost of just keeping something in orbit around the Earth, in terms of propulsion, that we're going to have to sacrifice volume, living space for the sake of reducing the mass. The shape is probably going to be different because depending on your propulsion system, you could be taking some pretty big, loads as rockets start and stop your trip to and from Mars. There's a whole range of propulsion systems. I think, the space station is made up of a lot of international partners, and I think, and now commercial components coming online as well, potentially. And I think we see that as also being part of a mission to Mars because it's such a big thing. We're going to need partners to do it. But I think many of us are trying to make it a little bit better integrated. The Russian sections and U.S. sections of the space station can be relatively independent. But and that's paid off for us to have a little redundancy sometimes. Mm-hmm. But I think we need a more unified, integrated system to be as efficient as possible for that.
Yeah, I think that's an important point because the ISS was built to be a lot of things to a lot of people. As you mentioned, it's a science laboratory first and foremost, and that also it's also how a lot of telescopes get designed. They have to be multi-purpose, be able to be used for lots of different science use cases, but here we're talking about a special use vehicle that is only designed to do one thing, that's get us to Mars and back safely. And we've talked a lot on this program about needing to use in situ resources on Mars instead of bringing it with us and things like that. And the ISS sounds like a really good platform for some of these technologies to be tested out. I'm always surprised at how things that should be they intuitively seem simple aren't. Like this, we keep coming back to CO2 scrubbers. That is still a big problem. Even if you change one tiny thing, like, well, now our astronauts have to exercise a lot more, which means a heck of a lot more CO2. I think you called it a metabolic load. I've never heard that before, but that I guess means more CO2, more sweat, more just stuff that comes along with the human body exercising, has to be handled efficiently with these new, even if you change just one small thing. So this is interesting, just how tiny how much everything is interconnected. What about?
Very much the devil's.
Go ahead. I'm sorry.
Well, I was just saying, and very much the devil's in the details on those things. So we may have very well understood the science of how carbon dioxide sticks to a zeolite, but physically designing the thing so that the valves operate even after long periods of time, or when they have dust in them, and the heaters do, scale up, and all of these things that are, industrial sort of problems, they matter. So the engineering matters as much as the sort of discovery phase of technology development.
That's really true. And
so
well, hang on just a second, Carl. The details are so tightly. It seems to me like they matter so much that the little tiny things could really make something that worked beautifully in orbit not work at all at Mars. How is there not? There just doesn't seem to me like there's much room for error here. What are your thoughts on that? I mean, you can't think of everything. Something's bound to go wrong. But if you change what do you think about just how tightly everything needs to be designed to get us to Mars and work?
So, I mean, I think Molly and I had a funny conversation on the way back here from Harley's conference. And, we talked about, hey, there's going to be risk, and we can't design everything perfect. We're going to do our darn best, but it's, it's not a simple thing saying we're going to send humans to Mars. We've never done that before. We send robots, right? We have not sent humans that far out.
It's orders of magnitude easier, isn't it, to send a rover?
And now you want us to land too. So yeah, there's going to be some risk, and there's always a trade there between designing out the risk, right, and designing to do the things you want to do. So some of the things, like in a conference this week, there was a couple comments about redundancy. When you want to land on the system, do you have two different Mars vehicles landing, or two different ones ascending for that matter, or is it all in one go? So it's always a risk balance. I think with any of the design that we're talking about, even with the CO2, there's a balance between the risk to the human health and the engineering that we can do with the mass budget that we have. So I wouldn't want people to think it's risk-free. It's actually
I don't think anybody. Yeah, no, I don't think anybody would think that. But sometimes it seems so overwhelming. It's just how much you've got to get right and how little room there is for error in some areas, and that was I guess right. Just sort of crystallized. Okay, Carl, I interrupted you. Did you want to say something?
Yeah, no, it's fine. Like, I think that's a really, really good point, because that's one thing that I've always noticed when I've gotten a chance to listen to briefings. It's like the devil really is in the details with all this. But there's a really great question when it comes to the next phase of testing that kind of I think y'all are both hinting at from Yurik on Discord, and he's saying, are there any other stations in the works to replace or be in addition to the ISS? And there's a couple other questions that are kind of along those lines in the YouTube chat as well, like what's going to happen after the ISS is retired, and the question is 2024 from Raj Lutha, but I think it's now 2028, or it might end up being that. But so what would be the next step to bring it to that hardware place where we can answer some of the questions that the ISS leaves open for missions to Mars?
You want to define end of ISS and what that?
Yeah, let's start there. Thank you.
So so Molly, I guess I'll start. And so ISS, people, you threw out the 2024 date. So 2024 is the date that we're currently committed to with our partners. It's not the day that ISS falls out of the sky. It's just basically a contractual or tree-based date. We've agreed to that with our international partners. We are right now in the process of looking at, okay, what happens next? In fact, Congress has directed us to come up with a plan to stepwise transition from a regime where ISS is primarily a government thing to when ISS has a more predominant commercial component. So we're still figuring that out. The lifetime of the parts is such that we could last till the end of the 2020s, and at that point, we have to replace the solar arrays first. So I don't know that it's a question of when does ISS end so much as how do we transition to the next phase. So that's why it's a great question.
Oh, so it's not so much ISS is going to be not up there and usable. It's going to be that NASA may not be the one operating it. NASA
may not be the dominant.
I see.
Now, we'll still be a customer. I think there's an ongoing, it looks like there will be an ongoing need for some sort of low Earth orbit platform for research, certainly, depending on what kind of training we might need to do for astronauts, or what further systems testing we may do. We may be a customer of some sort of LEO platform. But that's all the stuff we're still figuring out. I think the next step, I mean, NASA's talked a lot about a proposal to push out to some sort of habitat near the moon, in the moon's vicinity. You know, and we're looking at that. We're talking to, you know, the Space Council, the new administration, and all that about all those things. And it's one of our things about ISS is we really want to make sure we've tested the technologies we need in order to go further, as one of our indicators of, hey, can we transition away from this? And the other one is that, another thing is that we actually have that other platform in place. So I don't think you're going to see a full-on, hey, we're deorbiting ISS, we're done. You know, that's not going to be it. We envision whatever that next deep space platform is, that we will have a, I don't want to say peaceful transition, but maybe a gradual transition. So this is a big watch in space. It's probably the biggest issue. I won't say issue, but the most challenging topic in space policy right now is how do we take the next step?
Yeah, because there's so
many.
Let
me note something here. It was a little bit having to do with this workshop this past week, but loads of other workshops. And I think this is partially an answer to a question that you were citing, Tony, and that is that if there is a follow-on, well, there will be a follow-on to the space station. It will look more like the mission that we will send humans to Mars in.
Well, there's this cislunar thing I keep hearing about, right, Harley? We've talked about this before. That's it. Yeah. And cislunar is this idea. It means the area around the moon, and we're going to probably do something with that as a next phase. After
that's what it looks like. It depends on, and just as Katie was saying, depends on what, you know, if there's a budget and what the Space Council says and so on. So there's some serious decisions that need to be made. But the most likely outcome is, no, that's speculation. A likely outcome will be that perhaps a decade from now, there will be a habitation system, perhaps in the vicinity of the moon, in orbit, and it will look a great deal more like the habitation system that we will send humans in when we go to Mars than the space station.
You're not going to make it
that system.
Yeah.
You're not going to make NASA predictions, huh, Harley? Have X or W first? Which is it? Go. No, okay, all right, I get it.
Well, there's this old joke that those of us that have been in this business a long time. If you want to make God laugh, tell him your plan.
Yeah. Okay. All right. So let's see. The Raj Luthra has an interesting question, and I guess I'm curious about it as well, and maybe you guys could tell me if you're working on it. We've been talking about recycling urine, and he says, recycling urine into water is great, and that technology is being used around the world. More of the technology should be used in countries that have problems with drinking water. So that's one comment, so thank you for that. You guys, this idea of recycling has got to be one of the top priorities for going to Mars, right, guys? The technologies that recycle just about everything that can be recycled?
I have a hard time saying that, sort of. Right now, I think our top priority is reliability, but it is reliability of the technologies that do recycle things. And this is sort of a spectrum. People imagine that the best answer is a 100% closed system where everything is recycled. But realistically, right now, all of our food is sent from Earth. And you can imagine that as a slow and steady resupply of carbon, hydrogen, and oxygen in those packages, right? So there's water in your food. Your body generates water, from eating food and reacting it with oxygen. So you create more wastewater than you consume as clean water, actually. And so since we have all of this food anyway at this point, you want to look at where's the knee in the curve where it stops being efficient to recycle water or oxygen. You have to make sure that the systems that are going to do it weigh less than just bringing more of the consumable. including all of the spares and all of the pieces like that. So we have a pretty good level of recycling. If everything on the space station were working all of the time and we had this resupply of food, we'd be pretty closed. Now, when we get to the lunar surface, things start to change. It becomes a lot more expensive to bring the food. We are worried about whether the nutrition in the food can survive the entire journey. It knocks out sort of important vitamins and things like that. So we might end up with some grown food locally to supplement stored food. And then we're taking away a little bit of that sneaky resupply. Another question is EVA. And depending on where you're going,
extravehicular activity, is that what you mean?
Yes,
okay.
Right, spacesuits, yeah, sorry. All of the spacesuits we've used so far use evaporating water as their method of rejecting heat. And they all are relatively leaky compared to a metal spacecraft. And the crew has a very high metabolic rate, and they tend to use carbon dioxide systems that are carbon dioxide removal systems that are optimized for making it light enough to move around yourself and hopefully walk around in. And those aren't the ones that save the carbon dioxide for later use. So if you're going somewhere to explore and walk around in a suit or a pressurized rover, which is basically like a giant suit with multiple people in it, you're going to be taking a lot of water and oxygen and not bringing wastes back to the habitat. And so then things that we didn't bother recycling initially, we may need to do now because we don't have as many opportunities with those things that don't come back. So it's not so much about 100% closure. It's this sort of complicated balance of ins and outs, and how much did it cost you to get that versus just sending more of the consumable.
So, and can I add too, one of the other places though where we are looking at recycling is we're looking at like how can we reuse things like packaging materials to, basically for 3D printing. So you can print on orbit some of these parts, but so we're looking at having a multi-material capability where you can do plastics, you can do metals, you can print circuit boards. So those are different types of 3D printing or additive manufacturing capabilities, and trying to understand if and how they work in microgravity, and also things like if you want to use it for hygienic use, how do you sanitize it? So those are all interesting developments, but one of the challenges there is, those techniques aren't necessarily optimized for the kinds of parts that we need to manufacture there. And so you have to basically design the parts you're going to use to be 3D printed. So you have to know what you might want to 3D print ahead of time, design it to be 3D printed, and then also have the file so that when you want to 3D print it, you can. So there, NASA just had a solicitation for this. It is definitely something we're looking at. But it's not going to be perfect. So I know the Eclipse folks, Molly and some of the other folks there, the 3D printing folks would love the Eclipse people to adopt 3D printing. The Eclipse people are like, I don't know, our technology is too critical to be dependent on this thing that may or may not pan out. So this is kind of the fun of technology development. It's like, how do you weave all these things together?
Well, I think that's overall representative of sort of the shift in philosophy for how we deal with reliability and redundancy. The parts on the space station are very often packaged into what we call an orbital replacement unit. Mm-hmm. And you can argue how efficient they are, but the idea is that, hey, those astronauts are up there to do science. If something breaks, they just need to be able to pull this thing out and stick that next one in. They don't have to go fix it,
Right. So rather than giving you one part, you give the whole assembly and they just pull it out and stick another one in.
Right. But that's like, my battery's dead, so I'm going to replace everything that's in the hood of my car. Right. So for every, oh my God, how many times could something in your car break and you have to have a whole new car every time? That becomes kind of ridiculous. So we're trying to design these new systems so that we can get in there and just fix the thing that broke. Mm-hmm. And from a technology development point of view, it also requires us to have more capabilities in sensors and measurement so that the crew can at least take the measurements and send them back to the experts. Because when you're on your way to Mars, there's no way to send the busted part home to see what happened. There's no way to send a water sample home to decide, hey, it smells funny. Is that safe or not? You've got to be able to figure all of those things out in the mission. Data can go back and forth, but no samples or spares can. So it's going to be a big philosophy change in how you have to operate.
Well, sure, because if you think about this idea of repairability, things like as you mentioned, these modules in the space station, the Hubble Space Telescope comes to mind. It was designed to be serviceable, but it was like that. Pull out this whole huge chunk of thing, except for the last servicing mission for Hubble, which was a lot more intricate, and then shove this new thing back in. That's one level, but to be reparable on a Mars mission, I think it would need to be more like a human being would need to go, oh, you know what, this gauge is broken. Let me just fix this gauge and not bother repairing the whole computer or whatever it is that's broken. So I can imagine that the level of reparability has to change with the design, with what NASA's used to. But let me ask you this, guys. How conservative is NASA when it comes to designing things for Mars versus historically how it's always been? NASA really needs to get things right the first time for obvious reasons. We all want them to. We definitely don't want them to fail. But has it gotten any different in terms of, you know what, this is going to work within the error bars? Have the error bars gotten larger a little bit? Has there been any change in the level of conservatism at NASA when it comes to thinking about human spaceflight? I hope that question makes sense. Huh?
Only easy questions from you.
Yeah. So I don't think that we've made a decision yet, because it takes somebody, and that's a pretty dang high level of authority to say what % risk is acceptable in a mission, and it's a mission we don't even officially have yet. What we are doing right now is analysis to say, hey, if you want to get it to this level of reliability, you need 12 of those or 3 of those or whatever. Hey, if you want to have, this much certainty on your mean time between failure number, you need to test it for this long or that long.
Yeah, well,
and so
ultimately, it's
like preparing the trade space. Yeah, there are so many steps in a Mars mission that even if you did all of those steps with the same level of conservatism you do on ISS, the risk of the entire mission going well, it's very different.
Right, and I think there's a healthy tension there, internal to NASA in terms of, hey, let's just go do it, and versus, hey guys, we got to be safe, and that's good, that's important, because you don't want to, just, ignore all safety things.
Well, of course, yeah, if you listen to Elon Musk, Elon Musk actually scares me, because he just like, yeah, let's just do it, man. Let's just go. Here's my Tesla. I'm going to put that in orbit around the moon. It seems like it's really cavalier, and he's kind of scaring me with the way he doesn't seem to be as interested in safety. I know NASA is always interested in safety, but is it frustrating you said, I think it was Molly, you said that this isn't a mission yet. You're working on something that isn't official in so many ways. How do you do your job in that kind of environment? At what point is it going to be, who is ever going to say, you know what, NASA's going to Mars. Here's how we're going to do it. Everybody get out of the way. We're just going to go do this. And then now you're working on going to Mars. But it always seems to be like, well, we're going to the moon first. Well, we're going to the Mars. We're going to cislunar first. Maybe we'll build another space station. Maybe we'll just, it always seems to be moving around. Is that change much in how you do your job?
So, well, I don't think so, because Harley showed a graphic this morning at our other conference that cracked me up, because it was from what was it, 2001, Harley?
It was actually done in 2000, published in 2001.
Okay, and it was this proposal about having some sort of deep space gateway that then we use to go to Mars and to the moon and to build telescopes. Well, that's exactly the proposal that we've been working on now. So it seems like, I think we get wrapped up around the destination, but the goal of all that has been, well, how do you send humans farther out into space? further away from the support provided by the Earth. So I don't think ultimately that goal has changed. The details do impact the specifics of what are you designing to, but ultimately the goal is the same in my view. So it doesn't really bother me. I let the political stuff go, and I just keep moving.
Yeah.
Let me add something. Let me add something here. That I think if you step back a little bit and look at the last 20 years or so, I think, in fact, a very significant amount of progress has been made toward getting humans to Mars or maybe to the moon. Just consider, for example, what Katie and Molly have been talking about. There's been enormous engineering and technical advances, as well as operational advances, on the space station. It has been a tremendous engineering, management, and technical success. We are vastly closer to sending humans beyond the immediate vicinity of the Earth than we were 10 years ago. The SLS is being built. Significant advances in our heavy lift. Orion, the capsule that we're doing. Our commercial partners, SpaceX, Blue Origins, and so on. The world of space exploration with humans is vastly different than it was just a decade ago, thanks to significant work on the space station, launch vehicles, capsules, and so on.
Well, is that because, Harley, but a decade ago we had the space shuttle, that was our main thing, and now we don't have anything, and now we're looking at this SLS as sort of, well, we don't know exactly where we're going yet. Could be the moon, could be the Mars, but we know we're going to need to take people up into space and go a long distance, so let's build the SLS so that it can do either of those? Is that sort of the attitude? I mean, you said we've made a lot of progress over 10 years.
Yeah.
Is that the progress you're talking about?
That is one example. The list, I think, is longer than a lot of people give NASA and our commercial partners and our international partners credit for. We've known for well, I think probably well before that, but looking back on von Braun's architecture scenario for going to Mars that were in the Collier's magazines in the early to mid-50s, heavy lift.
Right.
One of the big solutions to sending humans beyond the immediate vicinity of the Earth has been heavy lift. And significant progress has been made on the next generation of heavy lift, SLS, or also the commercial options as well. So that is significant progress. We're not yet ready to push the button and send humans to Mars, but good heavens, we are vastly closer than we were even 5 years ago.
Right.
And when I started my career, we used to have to do these trade studies and say, how good is your advanced system compared to the state of the art? And it was funny, there was a phase in the middle there where our numbers were getting worse. And we went and looked at how the study was being done, and it's because space station state of the art was getting more and more credit for the advanced things that it had already adopted. So, the state of the art has definitely been moving on, and whether it's a big launch vehicle of some sort or the life support, the things human beings need once you lock them in the can are pretty consistent. Right. There's a little bit of change depending on if you're worried about lunar dust or something, but those are smaller changes, and we've made huge progress on the rest of them.
Okay, so what was it, Molly? There was a difference between what you had versus state of the art? Is that what you said? What you were currently working on versus state of the art?
Yeah, when we started, we'd have to say, well, if we introduce the advanced technologies that your program is funding, how much are you going to save in launch mass compared to the state of the art? Right?
Oh, okay.
And so when you compared them to the shuttle state of the art that had no recycling, it was hugely awesome. And then once you start putting the recycling into the space station and the state of the art moves on, now you're getting better at doing the critical function instead of adding a function that never existed before.
Okay, I just wanted to clear that. I was wanted to make sure I understood what you were talking about there.
Well, I
think Katie wanted to say something.
Also,
hold on, I think Katie wanted to say something.
Sorry, go ahead.
Did we cut you off?
Questions.
I'm sorry?
No, go ahead and have Carl ask the question.
Okay,
go ahead,
Carl.
And ask the questions.
Just one quick point for what we were talking about, like the redundancy and the risk and things like that. There's a really good part in the book, Rocket Men, when it's talking about the Apollo era. And they actually went into George Lowe's office, and we have to pick a number about the failure rate, and they ended up with 1 in 1,000, and then Apollo ended up being like 1 in 100,000 or something like that. But that's remained fairly consistent the whole way through. So it's not so much that NASA has become more conservative in its safety requirements. It's simply that the mission is more complicated, I think is probably a pretty good way of putting it. But one question can kind of flesh out Deep Space Gateway just a little bit more is, why would it be? It's from Bjorn Larson.
Hi, Bjorn.
What do you think about? What do you think about Deep Space Gateway? Isn't it smaller, more expensive, more irradiated than ISS? What would it be good for? So I was wondering if you could kind of answer a little bit about that. But one thing I think that's really cool about it that I saw in a proposal is that it actually has a Hall thruster on it, so we can do some of the planetary maneuvering that we would want to do on Mars and learn that in cislunar. So that's at least one thing that I know would be good for.
So the proposal for the Gateway is both Gateway and ISS would be doing testing of different systems. Gateway is proposed for short duration stays. And he's right, yeah, it's in a different radiation environment. That is actually one of the advantages of doing that. His ISS is protected by the Earth's Van Allen belts. So, we don't have a lot of data on things like galactic cosmic rays and what they do to humans and, for that matter, the hardware. So that is some of the advantage. I guess, Molly, on ECLSS systems, like Gateway, I thought we're just using the similar ISS systems for the Gateway proposal.
Yeah, there are many proposals for what Gateway could be. Mm-hmm. I think you have to look at the Mars mission, and a lot of the most recent ideas out of NASA for the Mars transit habitat have been that it should be reusable. I mean, reusability is certainly changing a lot in the commercial, in our commercial providers in the space industry. So that, to me, Gateway is like the pier, and the Mars transit habitat is like your cruise ship. And you're not going to drive the cruise ship to your house. There's a point in the middle at which you must meet. And so taking a big habitat all the way into Earth's gravity would pose a lot of challenges. So it should wait for us somewhere else that the Orion capsule or whatever can come and go from. So to me, Gateway is just sort of this node. It does have opportunities. We're not really testing new propulsion systems on ISS. We're happy with its orbit. So it does have some opportunities to test new things like the radiation or new propulsion at some scale. But then functionally, it becomes this node at which pieces come and go, and gives us just enough infrastructure to do that well. It doesn't have to duplicate all of Space Station.
So my husband refers to it as the Wawa. He also calls it the top tent, but it's like
I'm stealing that.
You can credit Colonel Bob, SMC.
All right,
and
well,
kind of along the lines. Go ahead.
Well, I just wanted to spend a few minutes. I just want to spend a few minutes on John Suffolk's comment here. He said, "I've said many times, a successful Mars program would need the cooperation most, if not all, the current spacefaring nations, including the private companies." And I think that's an important point. And so, Molly and Katie, is NASA thinking about international collaborations in getting to Mars? Besides, I know what SpaceX is doing, but is there a lot of thought going on about working with other countries to get us there and to help pay for it?
Oh yeah. So I mean, they're in the process of developing the next version of the global exploration roadmap, and we just heard from our colleague Kathy Lorini about how specifically they're trying to put forward a shared vision with our international partners. And that activity includes a lot of, I think, all of the current ISS partners. And I know, Molly, with the ECLSS, you guys have an international ECLSS systems team. And I don't know, you could probably tell us more about what they want to do.
So we have an international ECLSS team trying to collaborate.
Is that an acronym?
Intellectual.
Oh yeah, sorry.
ECLSS. I'm sorry. Environmental Control and Life Support Systems.
Thank you.
That's the acronym. Oh God, the acronyms.
I know.
So we have an international team trying to coordinate our technology investments, and share lessons learned and help each other's development as much as intellectual property allows. I guess it's sort of in the weeds, but one of the things I've been spending time on with that team is trying to draft an interoperability standard. Like we said, ISS is made up of lots of international partner components, but they don't all mix with each other for various reasons. And so, we are actively working with our international partners on a wide range of subsystems to say, what kind of standards would we have to put in place to really make a truly joint vehicle possible? For one of my concerns is I want to make sure that water delivered by any partner, any company, whatever, can go in the water system of any part of the vehicle. And right now, the Russian water has silver in it, and the U.S. water has iodine in it, and you can't mix them.
Oh, gosh.
So things like that. Like, let's not do that again.
Oh, gosh, that figures. Okay.
And that standards activity is it's a pretty large scale thing they're doing in general about coming up with interface standards. So it's not just for international partners, but also for our commercial partners. And so by defining what those are, well, then you can kind of plug and play as you do this. But you need to first write down, well, what is the standard going to be?
Yeah, I think that's pretty important.
We're definitely working on that. Yeah, and I believe that's going to go out for some comments, but I know they're working on that, even talking to our commercial partners about the standards and what makes sense there.
Okay.
So that's definitely in our mind.
All right, Carl, I interrupted you to get to that, so go ahead, please. I'm sorry.
No, that's really great, because that's one thing that I know has been, when I was interning, that was talked about a lot. So it's definitely going on. But the question is from Raja Luthra, which advanced propulsion research would be used in the future for human and cargo transportation, such as electrical propulsion, solar energy sails or electric sails, maybe firing lasers into them, etc.
Yeah, there's a lot of talk about the EMPs or the EM drives that go out, electric motor propulsion drives.
I think this is a little outside our area. So when I work for space technology, I work for Space Technology Mission Directorate, though. I know we're putting a decent amount of effort into the nuclear thermal propulsion. I think we want this mission to happen relatively soon. I think the major things in the trade space are the solar electric propulsion with xenon, some chemical propulsion, hydrogen or methane, or this nuclear thermal propulsion. I think those are the big near-term players for sort of first-generation human mission to Mars.
Mm-hmm. Yeah.
All right. Any other questions?
There's definitely talk at Stennis about testing that kind of stuff. No, there was one other one about the human factors when they return that I thought was very interesting. And I'll kind of broaden it out to concerns about future human factors, but they are looking at, say someone wants to become a parent after they come home from a mission to Mars. Has there been any medical research into the health effects once everyone's home that would enter into those concerns, and just more broadly the health of the crew once they've gotten back to Earth? And that was from Garrett G.
Oh, I thought for sure you were going to say Dr. Chris Lanehart, because he was quoted in Cosmo as they called him Dr. Space Sex because he was worried about human reproduction. So you have to actually put the split in between there because it sounds like SpaceX. But so I mean, it was a big question. So you're talking about the human health condition when they return. They do, in fact, I believe that's part of the twin studies tracking Scott and Chris this year following return. And I think there's probably still some more work to go. Our HRP people would talk about it a little bit more, but there is more effort on longitudinal health tracking of the astronauts. And I don't know. I think it's too early to say. Does the cumulative effect? We have a lot of astronauts have come and gone, right? Peggy Whitson's had some astronomical amount of time in space, but it's in several chunks. So I don't know if they're looking at whether that matters, or is it the one stay, is it cumulatively 365 days that matters, or is it, one 365-day shot that matters? So there's more work there, I believe. I don't know, Molly, I mean, you're closer to that part of it.
I know that, radiation risk is one of the big ones. And when those researchers study radiation exposure, you look at what could it do to all of the organs, including your reproductive organs, and it's part of the risk assessment. I don't know that we've ever had anything particularly focused on them. I'm pretty sure Karen Nyberg talked about she, flew into space, and then she had a temporary medical condition, and then she flew into space again. And, her temporary medical condition is now, 3 years old and likes Legos and whatever. So we've had astronauts
we've had astronauts
got pregnant and flew again. That has happened. Those are, the ISS missions.
Yeah, and I suppose, I mean, we do research on station with flies and with rodents and things like that. And, I can't remember if there's a reproductive study there, but that's another way you could use ISS to understand those things.
Wow,
I've seen a lot of slides of mouse ovarian tissue.
Wow, we've got a long way to go before we get to that point, I think. All right, folks. Well, that is it. We run out of time, and I want to thank my guests so much for taking time out to talk to us about the ISS role and getting us to Mars. A lot of work going on. A lot of work will continue to go on, both within NASA and internationally, because it is the International Space Station. So there'll be a lot of work going on getting us to Mars, and I'm sure Harley will help us keep informed on what's going on. With future efforts to getting us to Mars. We'll see you, I think, next month, although that coincides with the AAS meeting in January, so I'm not sure we will have a hangout then, but if we do, I will make sure to post it. We will not be having an Astro Coffee hangout next Thursday because we've had some cancellations because of the holidays and things like that, so we won't be having one next Thursday, but I am hoping, if I haven't asked John or Adam or Alexander about this yet, but I'm hoping to have a telescope talk hangout on Wednesday. But if we do that, then we'll have that next Wednesday. We'll talk more about telescopes coming up on the Christmas season, so we'll try that out. Harley, is this it for the year, do you think, or do we have another Future in Space?
We will have our astronomy talk on the third 2 weeks from today.
In 2 weeks, okay.
And I think we can broadcast from the AAS meeting, which is right across the Potomac from where I am here.
I think you can, yes, if you're going.
So thank you very much. Also, by the way, I think we did have, wasn't one of our first hangouts, a Sex in Space hangout with, but at a serious level. Wasn't that Betty Siegel and was that John Charles?
But yeah, Betty can talk very well about the differences in the impact on gender. She talks about that.
Okay.
So it is an interesting topic, and it is liable to giggles, but it is very serious work.
It is, and I'm sure there'll be lots of volunteers also. I'm sorry, I just had to say that. Okay, that is it for this. That's it for this year. We will be back in 2018 with the next Footsteps to Mars hangout, probably from the AAS. Thank you, Harley Thronson, and also on behalf of my guest, Dr. Katie Boggs. She's from the ISS division at NASA HQ. Also, Dr. Molly Anderson. She's a life support development specialist at the Johnson Space Center. Thank you guys so much for taking time out to talk to us about what you're working on for getting us to Mars. And we'll see you guys next time. And as always, keep looking up.
Looking up. Great.